So this week's rockstar is Simon Jowitt. So Simon's economic geologist and is currently an assistant professor at the University of Nevada, Las Vegas. And I'm so grateful that he could join us today to chat about the current and future trends in base and critical metal demand and the implications of the energy and transport transition for the global mining industry. So thank you so much, Simon, for joining us. It's absolutely wonderful having you.
Cool, no worries, and thanks for inviting me to give this talk. So yeah, as Jeff just said, I'm going to talk a little bit about current and future, about what you can see on the screen. It's a long title, so I'm not going to read through it again because that'll just take up half the talk time. So basically, what I want to talk about a bit today is something that basically something like the title of this slide. Mining is old, dirty, problematic, and we don't need it. And this is a Bingham Canyon just up the road in close to Salt Lake City, one of the world's biggest copper mines. And this is what people tend to think of when they think of mining. It's like, well, this is kind of something in the past. We don't need this anymore. But hopefully everybody in the audience disagreed with that, especially this audience, because we should all know that mining is kind of crucial to modern life. But even in Australia, a country that's very familiar with mining, mining is heavily involved in the economy. Comparatively few people acknowledge it or even think about it. And you had protests at IMARC in Melbourne in 2019, protesting generally about mining, and people thinking that this is kind of thing of the past. But if you actually look at the literature, even going back to the 2002 World Summit on Sustainable Development with the UN, this is back in 2002. So, mining minerals and metals are important to the economic and social development of many countries. Minerals are essential for modern living. We all know that mining has been vital to modern life and society for centuries. It's going to remain so for this foreseeable future, and it's going to be needed if we have any chance of, improving the standard of living across the world and meeting things like UN Sustainable Development Goals. This last sentence is, what we all in this audience know, but it's not what I would argue the general public knows or even thinks about. The general public thinks about stuff like this. Mining is a big hole in the ground. It's old, dirty, and problematic, and we don't need it anymore. And people often say things like mining is dirty, harms the environment, harms people. This is what us as economic geologists or people involved in the minerals industry are kind of up against most days. The fact that this is a generally held view. This might be the case in some areas, but we all know that mining companies are doing a better job of environmental assessment, cleanup than in the past. They're more socially aware. Mining can provide communities with benefits, and equally, mining companies, because of things like environmental, social, governmental risks, they're having to be more aware of this if they want to continue to operate. Things can always improve, but the mining and minerals industry is coming to terms with these challenges, and these challenges aren't going to go away. So we should. We can tell the general public that things are going to become even better if mining companies want to continue to operate. But one of the things that I'm kind of talking about in the title of this slide is climate change and mining. If we want to do anything about climate change, anything about limiting carbon dioxide emissions, we're going to need more mining. And I'm sure people have talked about this in you've heard of this in the news, you've heard probably people give talks about it, you've read it in publications and so on. And I'll just summarize some of the data that's going to back up that claim shortly. Before we get into that, just as a kind of brief reminder to you all, why modern society needs mining. This is something that the Minerals Education Coalition in the US here produces every year. It's called the Mineral Baby. It basically shows what every American born in this year, in 2020, will need, in this case, 3.19 million pounds of minerals, metals, and fuels in their lifetime. Because you're an Australian audience, I've converted everything into metrics, so you don't have to deal with these horrible imperial pounds and gallons and so on. But the bottom line is here that this kind of emphasizes that every American, every person born or every person living will require an awful lot of metals, minerals, and so on in their lifetime. And these numbers, some of these numbers decrease somewhat, like coal decreased over time, but the vast majority of these numbers stay the same or increase. Because we as a society are becoming more mineral intensive. Why is that? It's because we've gone from things like this this 1980s standard smartphone to this on the not very smartphone. What's the opposite of a smartphone? A brick. To this thing on the right, like an iPhone. And the color coding on the periodic tables at the bottom that just indicate the variety of elements that are in these two consumer devices. On the left, we have a fairly wide range of elements. On the right, we have the same elements, plus a whole bunch more, which has made this phone a smartphone. There's been a decrease in some things. There's less beryllium and less lead, but there's been an increase in, almost every element in the periodic table is represented in this one consumer device that we all take for granted. You're all watching me on some sort of device that probably has a similar range of elements in it, especially if it has a touch screen, a lithium-ion battery and so on. Similarly, this is one thing we need to think about if you think about climate change is, green or renewable energy. We take an example of a wind turbine here. We look at the makeup of an average wind turbine and, you need 4.7 tons of copper, 335 tons of steel, 1,200 tons of concrete, 2 tons of rare earths, all these things that are having to go into these developments that we're seeing to move towards a kind of lower carbon dioxide, lower CO2 emitting society. So that's kind of a few examples of how the things we take for granted as, everyday modern life requires things like metals and minerals. They're the material basis for modern society, and that's something that gets lost, I think, in a lot of people's mind. They don't think about it. They just, enjoy their car, their house, their apartment, their modern conveniences, and they don't think about where the raw materials come from to actually enable those things to exist. And this is, combined with increases in population, is why we mine more than we in metals and minerals, basically anything apart from, odd exceptions like, say, asbestos. This is why we mine more of everything than we have at any other time in history. And this is an underlying trend that we're seeing for the last century plus. I've got a few examples of this. I'm not going to go into these in detail, but if anybody wants a kind of backup data that shows this, then I'll happily pass them on. Just fire me off an email. But this is one example. This is gold up to about 2015. We have a fairly flat with a couple of peaks of gold mining back here in the past, dominated by South Africa for much of this time. This is about 100 years of gold production. But then you see about the 1980s with changing or increasing gold price at around 1980. And that gold price hasn't significantly dipped, or much at least from the time from the 1980s onwards. Certainly not in the last 10 years or so since the global financial crisis. But what you'll see is just basically everything, global gold production has increased to, this is in 2015 to about 3,000 tons, and we're north of here now. Similarly, think of another metal. Let's have a look at copper. Copper, this is copper to about 2013. 2020, copper production was about 20 million tons. So we're about here, maybe even off the top of this slide. But again, you can see as we've, as essentially modern life or the standard of living of everybody in the globe has increased or improved in some way over the last century, that has required a huge amount of mining, a huge amount of metal extraction, a huge amount of change in the way we mine to actually enable this extraction to occur. You can see Chile with the giant porphyries down there is dominating copper supply, but there's places like the US, Canada, and Australia, even Europe, there's significant amounts of copper production in all of these places still. Another example, zinc. Again, we have the same trend. And as I said, you can do this, you can show this for any metal you think of. There's even some of the critical metals like the rare earths, you see a similar trend. Basically, what we're seeing is an overall increase in production of metals over time, especially over the last century. All these the metals I've shown, if you'll go back to about 1900, 1915, there's a slow increase over time. But then what we see is, I'm not going to say exponential, but a very rapid increase over the last century, half a century, depending on the metal and its uses. And this isn't stopping. This is the trend that we're seeing continuing to the present day. And this is something that is underlying the global minerals industry, this increased production and hence increased demand for almost every metal we see in the periodic table, and minerals as well. Things like fertilizers and the like that you don't typically consider to be metals. So we mine more. Does that mean we're running out? And this is a question that I'm not going to delve into in any detail, but what I just want to show is a few examples here, a few more graphs. There's not many rocks in this presentation, but there are a few graphs, I'm afraid. But what we've got here is just graphs showing reserves over production. So this is global reserves of a given metal, or iron ore, or bauxite over annual production. So in other words, this, in essence, shows the number of years left if you just consider it to be reserves, all that we have in the ground, which is crap. But, let's just take that as an approximation. What you see is you've got a bit of variability in the data, but what tends to happen is as you go through time, things flatten out. You can see all these commodities here flattening out as we approach 2020. Same with here, copper, lead, nickel, tin, and zinc all flattening out. There's some trends that go down, like cobalt goes down like this, which is potentially a little worrying. But everything else, you've got generally flatline trends, and certainly nothing getting close to kind of this real base level here, which is when you might start to panic. So this is, the data are noisy here, but in general, reserve production ratios have been fairly steady for the last 30 plus years, especially for major metals. Some volatility in minor metals. This might reflect poorer data. We're not actually capturing all of the production or all of the reserve rather than actual variations. But what this is telling us is that even with that increased production, we've actually managed to continue to delineate reserves that are at the same rate, essentially. So we're not running out of reserves of copper because either the replenishment or the delineation of known copper reserves is matching increased production. And this is another way of looking at that. What this is basically showing copper resources along the, ignore the spelling mistake, but copper resources in 2010 along the x-axis, as along with cumulative production. This is 2015 mineral resources for exactly the same projects. What we see, if you plot them all, some projects have decreased in size, so they've lost resources or they're becoming exhausted. Some have increased in size relative to their point in 2010. But if you put a best fit line through all of this, it's a slightly positive slope. In other words, if you look at copper data for 2010 and 2015, just the projects that existed in 2010 and existed in 2015, these projects on average have increased in size by about 13%. So in other words, you have 10 million tons of copper in the ground in a project. It's a very large project, but if you look at the same project 5 years later, you account for production, that project on average has increased in size by 13%. So it might be 11.3 million tons rather than 10 million tons or so. What does this tell us? This tells us that reserves are generally steady and resources are increasing through brownfield expansion. In other words, as we convert our resources to reserves and production, we're matching that throughput by adding more resources at the other end. In other words, we're delineating, reporting more of the project, more the mineralization we know is in the ground already. If you add into this, new discoveries will add more metal to this mix. So in other words, what we're seeing here is everything is good, right? We're not running out. We're producing more than we ever have done before. We're pretty good at discovery, so we're adding more of that to this mix. And so everything is looking pretty good. We don't need to worry about all this increasing metal demand that we're seeing continuing, and that's likely to increase in the future. Not exactly. So, that isn't exactly the case. One thing to think about is that kind of wind turbine for one. The other thing is, we'll talk about ESG risks as well. But, what about the future? What about climate change? The climate change might be a dirty word amongst some of you, but I'll discuss that shortly. But if we have any hope of meeting carbon dioxide emissions targets, we're going to need more mining. We're going to need to move towards green, renewable, low carbon, zero carbon energy storage and transport. The move towards electric vehicles and renewable energy that we're seeing already is making this demand increase inevitable. It's happening already. It's a global change. It's not going to stop. Electric vehicles require more metal than petrol vehicles. They're heavier. They require more copper. The battery systems require a large amount of various metals. And equally, there's no point having an electric vehicle with electricity generated at a coal-fired power station. It's worse than a gas-guzzling petrol SUV. There's no point in having that sort of approach and having that sort of system if you want to do anything about climate change. The other thing is at the other end, that we're talking about, this is the demand end. At the supply end, the minerals industry is seeing more, environmental, social, and governmental risks and challenges. So this means that, in the future, we're likely to see more mining projects being delayed or even being sterilized. Basically your resources are no longer resources because you have no hope of extracting them because maybe somebody's considered that, that area is no longer suitable for mining, etc. So there are a few of the risks that we're seeing, and then also a few of the kind of things on the demand side. Equally, this isn't news. This is a news article from the 24th of May from the BBC. Moving towards net zero inevitably means more mining. Richard Harrington, colleagues at the Natural History Museum, says that we need to kind of have an urgent conversation about where and how this new mining that we're going to need is going to happen. But this isn't new. This is something we've been talking about for over a decade. We're seeing these new emerging trends, or these trends that are they're not emerging, but they're speeding up in the form of demands for EVs, green energy, and so on. Moves to make fossil fuel emitters and producers like Shell or ExxonMobil more accountable. These trends aren't going to go away. They're being driven by consumers, by investors, by money. They're actually there, and they're not going to change. You again, as an audience, might think this is obvious, and it is. But to the general public, this is news. This is why this is headline news on the BBC. Right? We've known this for more than a decade, yet it's still making the news. And that's because, in essence, this information has somehow not sunk into the public, probably because they don't think that mining is important. It also hasn't, worryingly, sunk in with policymakers, or maybe it is just starting to sink in. But to me, I'd like to get some of your opinions, but to me, it still seems like an uphill battle, having to explain why mining is important, having to explain what is going to happen over the next 10, 20, 30 years if these trends continue and so on. And this is one of the things I want to emphasize is that we need to have wider conversations, because I can talk to you in the audience. You know a lot of this already. You hopefully agree with some of what I'm saying, maybe not all, but at least some. But the fact is that we need to have this conversation more widely. And this is one example of which, but this is news for a day, then it's going to go away and people will forget and go back to thinking mining is old, problematic, dirty, and we don't need it anymore. And there are some people, maybe even in this audience, that don't believe in anthropogenic climate change. First up, science doesn't care whether you believe it or not, but I'm not going to get into that argument today. What I'm going to say is we're already shifting to low and zero carbon dioxide, CO2, energy generation and transport. The trend is happening. The trend is being driven by money, investment and consumers. And this is where Australia, as one example, could potentially become a leader as well as a supplier of raw materials. There's opportunities here for people to actually, shift where they are rather than just being a supplier of raw materials. Maybe you could become a leader in actually, the entire kind of value chain after mining rather than just mining itself. This is a global movement. We're seeing it globally. It's going to continue. It's being driven, as I say, by consumer sentiment, investment funding. We see these trends happening, and you can either get on board with them, irrelevant of what's causing them, or you can ignore them at your own peril. And the other thing is metal mining, processing, green tech, energy development, and all of this will more involve the production of high-value raw materials and the generation of even more value down the mining chain. If you look at the value add for mining, it's not mining the raw materials, it's downstream where you turn those raw materials into manufactured goods, technology, and so on. There's a potential to generate a lot of well-paid jobs that actually could boost the economy. We saw that in the late 2000s mining boom down under. Maybe we'll see the same again. It might last for longer, and equally you could potentially have a lot of value add down the mining chain. So now we all agree that these trends are happening irrespective of whatever you think about climate change. One of the things to think about is what's going to happen with these shifts to low or zero CO2 energy and transport. What we're going to need to do is reduce CO2 emissions. This is just going back to the climate change. This is one of the main drivers for this. We need to reduce them significantly, and this is what policymakers are thinking about. We talk about 4 and 2 degree temperature increases, but for the main point of this talk, what we're going to look about is how much carbon dioxide we need to remove from, or not remove, but prevent from being emitted. So, what we need to do is basically we need to remove or reduce cumulative carbon dioxide emissions by 2100 by a third, which is a pretty tall order. So we need carbon dioxide emissions to decrease by 60% in 2050 and to decline towards neutrality after that. How do we do that? Low CO2 energy, low CO2 transport, and so on. So let's have a think about cars. So this is a typical car, vehicles, typical amount of copper in a car. There's obviously other metals as well. We have a nice internal combustion engine here, 48 pounds of copper. Again, apologies that this isn't in metric, but I can't do the conversion in my head in a minute. But what we have is 48 pounds of copper in a normal petrol-driven vehicle. Hybrids use 88 pounds, and a battery vehicle, Tesla or whatever, 183 pounds. So this is a huge increase in the amount of copper within a given vehicle. And if you're replacing the entire world's stock of vehicles by electric vehicles, then obviously this is going to be a huge amount of copper. And just one metal, there's a huge amount of other metals that are needed as well to actually meet this. This is there's two things driving this, as I say. There's carbon dioxide reduction, but there's also consumer sentiment. People are starting to look at electric vehicles more seriously. You can see that with the best-selling vehicle over here in the US is the Ford F-150 pickup or ute, as you might call it. They brought out an electric one, and we'll see how that does. But that's the best-selling vehicle that Ford have in their fleet here in the US. And I suspect it's going to do pretty well when people realize how useful those vehicles are compared to the petrol-driven ones. We wait and see, but these are the things are going. And this is the things that we as people in the minerals industry need to think about, because this is where demand is going to come from. If we do a back-of-the-envelope calculation, currently global vehicle production uses about 1 million tons of copper a year, 5% ballpark of copper production. Only 1% of these vehicles are electric. If we go all electric by 2050 or 2060, say, let's push the date back a little, electric vehicles need 4 times as much copper as a petrol vehicle. If we go all electric, we don't assume any more vehicles on the road, which is a big assumption. The global car industry is going to need 4 million tons of copper production a year. 400% increase from now, 20% of global current copper production. That's a big jump in say, 30 years. Only it's more, because electric vehicles need infrastructure, they need renewable energy sources, they need all this stuff, which all involves copper, because that's the way we transmit energy and electricity. All of this needs to be thought about as well. So what we're going to see if we go all electric vehicles is a huge demand increase for copper and all the other metals as well. And then we build in energy generation and all these other sectors. So, this is lithium-ion battery packs in electric vehicles. So we look at this is thousands of metric tons. This is where we are about now. Maybe essentially 1 million tons of metals in lithium-ion battery packs in electric vehicles. By 2030, you're talking about getting on for 7 or so, 8 million tons or something like this. And this is manganese, lithium, coal, all these metals you see here, some of which we produce quite a lot of, some of which we don't produce much of, like lithium right now. But you see there's a huge demand in metals just for electric vehicles, just to meet the change in demand we're seeing already. If we think about energy, this is energy tech alone. This is in the World Bank. This is our annual production in 2018. This is the projected annual demand from energy technologies in 2050. Annual demand for energy technologies alone. So what we're doing is, you're increasing cobalt production, you need to increase by 460%. Not cobalt use currently in energy systems, but cobalt use, all cobalt use. So in other words, we need 460% of our current cobalt production is going to be, this is going to be annual demand for energy technologies per year. Yes, there may be increased recycling, if we have more cobalt in the stuff we use or the stuff that generates power or battery packs. But, the numbers on the right, some of these percentages are pretty staggering. 99% increase in global nickel production for energy tech demands alone. And this is the challenges and opportunities we as a people in the minerals industry are facing. This is what we're looking at in terms of this is business as usual kind of demand right now. Demand, we're talking about the annual average demand of minerals full stop will increase to 1.8 billion tons if we don't do, if we don't see any meaningful or any significant changes in renewable energy and electric vehicles and so on. But, if we try and hit carbon dioxide emissions targets, or even if just consumer demand dictates that we move this way, then we're talking about, doubling the amount of minerals and metals we currently produce on an annual basis. So, if we think about deploying wind, solar, and geothermal power, I don't know what it's like in Australia at the minute, but even here in the US, there's a huge amount of this going on already. Texas is the largest wind power state in the US, unbelievably. So, we're seeing big changes away from fossil fuels and moving into renewables. If we do this in a meaningful way, if we actually hit the 2 degrees target, or even if consumer demand just dictates, we're going to see 3 gigatons of minerals and metals are going to be needed just for these technologies. So what we're going to see, what we think we're going to see is a whole load of mining, lots of mining, but there's also a few other things that have been talked about a lot, I know, down under. So if we go back a few slides, there's metals like neodymium, lithium. One of the questions is, where do we get these from, and can we meet demand for these, these critical metals? And this is another source of a challenge, another source of a problem for a low carbon dioxide, or just a future where consumers want electric rather than petrol vehicles. We talk about the critical metals. There's a lot talked about these. I'm not going to go on this in detail, but in essence, there's no strict definition of what they are. It depends on your viewpoint. But what we know is they provide essential properties to a technology or product, especially advanced technologies, advanced like low carbon dioxide technology and energy generation. You can't substitute for them. You can't just swap in another metal. You can't recycle them, or we can't at the minute. They're generally not recycled in a meaningful way for most critical metals. And they're subject to supply chain risk, and they're often strategic as well. So not only do they have low CO2 uses, but they have military or energy and military uses. One example is the rare earth elements. They get talked about a lot, and there's a reason for that. It's not just because they're very critical, but also it's because they're an example of a way we can actually communicate with the general public. People want to talk about critical metals, they usually pick rare earths because people know about them now. And that's an interesting tactic. And when there's other metals which are just as critical, but are often don't make the news because people don't know about them. So what do the rare earth elements do? They do things like this. This is dropping a rare earth element magnet through a copper pipe. You dropped a normal magnet through here, then it wouldn't slow down. It wouldn't have this interaction with a pipe called Lenz's law. But what you can see here is it's been slowed by interaction, the magnetism of the magnet interacting with the pipe. As well as having fun uses like this, it's what makes your hard drive in your laptop work effectively, or the magnets in your wind turbine work effectively. The magnets in your hard drive, or the magnets in the generator in your wind turbine work effectively. So you can have lots of fun with these magnets. I'm not going to dwell on this in much detail. There's lots and lots of videos available on YouTube. But as I say, this is what happens when you essentially dope a magnet with neodymium rather than just having a normal kind of magnet made of base metals. And you can have fun with silly putty as well, where they're basically the magnetic putty, or the iron-bearing putty kind of swallows up these neodymium magnets pretty effectively. But to go back to some of the kind of more semi-serious stuff, I'm not going to go through this in detail, but one thing I want to know is this is what's driving all these critical metal usage. We've got things like low emissions energies, production, storage, usage, and so on. And these are the metals that are being used. And everything in bold here is essentially a critical metal. There's a lot of them. They have a wide variety of uses, but you do see the same ones occurring again and again as a result of even driven by different things. When you put all these drivers together, what we end up with is a huge range of increased demand for these critical metals, among the demand that we're going to see for things like copper, nickel, and so on. This is one example. This is just looking at neodymium in wind turbines. There's a few different models here, but basically what you want to take away is this is the current annual neodymium production here, 7,000 tons a year. This is cumulative demand through to 2050 for different levels of rollout of wind turbine technology. So this is the 2-degree scenario. So this is the most wind turbines, different types of wind turbine, but basically what you're seeing is 50,000 to 200,000 to 400,000 tons neodymium to generate or develop all of these wind turbines. This is just wind turbines, never mind every other use we have for neodymium. And this, you see this again and again throughout most of the critical metals. So, we know that they're crucial for these technologies. They're crucial for things like everyday life, like your smartphones as well. So there's an awful lot of competition for these critical metals, which is another factor in this. But, to summarize, if we want to move to a lower carbon dioxide future, if you want to meet consumer demand for these products, we're going to need lots more metal, especially critical metals. And these trends are happening already, as I've mentioned. This is one example, again, from the BBC. This is 2 days ago. Talking about why electric cars is going to take off sooner than you think. It says here you probably haven't even driven one, let alone buy it, and thought about buying one. So the prediction is bold, but basically what we think is going to happen is that electric vehicles are going to take off or become more commonplace much more rapidly than we imagine. What some people are suggesting is that this is the kind of new products, the S curve of new products. We have years, we have the market fraction from essentially no electric vehicles or no use of technology at all, or given technology, to 100% use. What we think is happening is we're reaching this tipping point here where we're starting from, we're going from the slow growth period to exponential growth as prices fall as a result of, economies of scale and technological advances and so on, until we hit market saturation where essentially everybody has an electric vehicle. This is the driver. And this applies to all sorts of different things. It's not necessarily because we want to hit carbon dioxide targets. It's because people more and more want a Tesla or a Ford F-150 Lightning or whatever it's called. These electric vehicles, they're going down in price. The charging places are appearing more and more. They're becoming more fashionable. People talk about Tesla all the time. 5-10 years ago, not so much. 5-10 years ago, we were probably down here. Now we're around here. Some people suggested this tipping point where we may start to see exponential growth. And what sort of demand is that going to have? What sort of effect is that going to have on the minerals industry? It's going to have a huge effect on the demand for certain metals. We know that, we can talk about copper, we can talk about nickel and their demands as a result of EV uptake, but the critical metals are in some ways more important for this technology, like lithium, like neodymium and so on. But few of them are produced as main products, not byproducts. That means they're almost always dominated by extraction at smelters and refineries as byproducts. It means that quite often mining companies don't think about them as being valuable at all. They may not report resources, even though they produce them. And that creates a lot of confusion over how much critical metal production there is, how much we have left in the ground, and so on. Again, this is an opportunity. There's lots of critical metals that are currently going to waste rather than being produced. It's a function of economics, the mineral processing approaches used, or just lack of understanding. We don't know where these metals are. Sometimes they come out at one end, sometimes they end up in the waste pile. We're improving, but we still don't have a good handle on why that is, or what we can do about it potentially, or why we should, because there are economic benefits of doing this, and I'll show in a case in point of that shortly. The other thing is resources are unreported. We don't know we know deposits produce these metals, but they're not stated in resource reserve reporting because the economic benefits, if you look at JORC, the economic benefits dictate that they're fairly minimal, so they don't typically get reported in official resource reserve estimates. Other thing to note is that these things don't get recycled. Less than 1% recycling for the rare earths. In general terms, not always, but in general terms, most critical metals don't get recycled. And that's another problem, and that's just the way they're used in small amounts in designs or end products that are not easily recycled. So this kind of summarizes the problem with some of the rare earths. We have our main metals in the middle here, things like copper, nickel, iron, titanium, platinum, lead, zinc, so on. And these elements around here are the elements that are produced as byproducts of these products in the middle of this wheel. If we look at copper, almost all selenium and tellurium production is a byproduct of copper production. Almost all cadmium and indium production is a byproduct of zinc and so on. That means that if you want to increase more tellurium or increase more indium, you need to do something with the zinc sector. You don't start an indium sector of mining, you do something with the zinc sector. You try and improve your production of indium from your zinc concentrates and ores. Put it more simply, this is just a table showing exactly the same thing in some ways. The copper, and here's our byproduct elements. This indicates the sectors of the mining industry that the production of critical elements are reliant on. In other words, to ramp up critical element production, we need to do something about these sectors of the mining industry. Maybe we'll see more like cobalt or tellurium production because we're ramping up copper production, but that's not necessarily the case. The other alternatives, if zinc demand drops off for whatever reason, we're going to lose production of a whole lot of elements we need, like indium, germanium, cadmium, and so on. You need indium for your touchscreen on your smartphone and various other uses. So if we lose production because zinc production decreases for whatever reason or just flat lines, then what we might see is a problem with some of these critical metals. Other problem is that we don't know, they're not well quantified. We know some of them, we know few critical metal resources, we don't know all of them. There's a lot of uncertainties, and this kind of gets back to the question of security of supply. How do we know the criticality or what resources or reserves of metal we need without knowing where it's coming from and how much we've already got? It's very difficult to try and produce more of these metals if we don't know where it's coming from. And this needs more work in essence. So this is another opportunity in this case for research, trying to understand where these metals come from, their material flows through the kind of mining chain and into end products. We can recycle them as well. It's a great idea. We recycle a lot, but not all metals can be recycled. And equally, recycling can't always meet increasing demand. And this is something I'm sure you've heard lots of when people are arguing against mining. It's like, why can't we recycle more? It's very difficult to use recycling to meet increased demand. Things are, you've got a certain amount of metal in stock that reaches their end of life each year. We recycle as much as we can. We can't all of a sudden just increase recycling to meet increased demand. It doesn't work like that. We know that, but the general public doesn't. And that's something, again, we need to have more conversations about. And the other thing is product design. Your iPhone here, product design means that a lot of the metals within something like that is simply not designed for recycling, so it's going to end up at a landfill. I could give an entire separate talk on this, but don't worry, I'm not. I know you guys have got other things to do later on in your day, so I'm going to leave it at that. But it's just an important point that we need to, again, express to people that you can't just recycle stuff to meet increased demand. It doesn't work. And there's a whole lot of other challenges to think about, but these challenges also represent opportunities. Finding mineral deposits to meet increased demand is not necessarily easy. Ensuring to make the most of these deposits is going to be an increasing challenge, and there will be increased demands of this because people are going to, as people become more aware of the critical metals and so on, they're going to say, well, what's happening to them all? We know they're in these mineral deposits. Why aren't they coming out the other end? Waste rock and tailings are issues, challenges as well as environmental, social, and governmental challenges to mining. And there's NIMBYs and bananas I've put here. So NIMBYs are not in my backyard. So that means, let's say, people in California who want their solar power and Teslas, but don't want the raw materials extracted anywhere near them. So yeah, it's great, but don't do it anywhere near me. Bananas are people who say, build absolutely nothing anywhere near anything. So just stop doing stuff. Efficiency is the way forward. Let's not bother actually mining more materials. And that doesn't work either. So this is, arguing against these people is like arguing against Donald Trump. It's futile in some ways, but we have to give it a go. And you can't continue just shipping your problems overseas because you also in some ways ship the value, but then what happens to the problems that you ship to, say, processing in China when the Chinese say, no, we don't want to do this anymore. And then your supply of metals become jeopardized. There's other problems. I know there's going to be a couple of talks about industrial minerals later on, I think, in this series, but things like concrete and cement are huge CO2 producers. Equally, metallurgical coal, as everybody knows, coal is now bad, full stop, but we still need it to produce steel. There's some replacement activities going on, but we're not there yet, and we're going to still need metallurgical coal for steel production. That's a given. It's a fact. You need coke for blast furnaces and so on. So we need to, again, explain why we still need some of this coal to be mined out of the ground and used. And that's another uphill battle that needs some work, I would say. Just to kind of wrap this up, I tried to outline a few future trends in a fairly short period of time. I might have gone over a little, but the bottom line is, if you want to do anything meaningful about climate change, you're going to need to mine more minerals and metals. Creates other questions, problems, and lots of opportunities, I would say. Where we're going to find these metals and minerals, what impact is this metal extraction going to have, and how can we do this? We need to educate, we need to do more research, we need to have open conversations about this beyond the minerals industry. There's all sorts of things that need to happen, and we need to make the public more aware of what they require if they want a modern standard of living, and we need to ensure that they realise that if they want to carry on in certain ways, then this is the actual cost of it, and an opportunity for the minerals industry to work in this space. So, if you're not already convinced, I know you guys are, but every single person listening to this talk needs mining. You all know this, but we need to educate the rest of the public. And I know Pete Betts and others are doing this in a number of different ways. Any sustainable future with reduced anthropogenic climate change, lower CO2 emissions, is going to be built on the back of the mining industry. There's no point having EVs fueled by electricity generated by coal. It doesn't work. It's worse than having a petrol vehicle. And if your attitude is climate change doesn't exist, then we're going that way anyway. These trends are global. They're occurring increasingly rapidly. The world is moving towards renewable energy and electric vehicles. This is a chance for Australia to become a world leader if it wants to be, or alternatively, you could turn your back on this opportunity and these trends that we're seeing anyway, and see what the future brings as a result of that. Demand for metals is going to increase. Does Australia want to be the world supplier of raw materials, or home of high-tech manufacturing as well as the world supplier of raw materials? If the latter, you need to rethink about where ores are processed, why things are done, and so on. So these are questions for politicians and policymakers, but it's important that we actually have this conversation and they understand the decisions that they make, because I don't know about you, but I don't think politicians do understand the decisions they make at times. Casting a few aspersions in this area. We're already seeing changes. So on the left, we've got the Australian government promising a roadmap for processing critical minerals, but there's enormous challenges. On the right, this is developments at Bingham Canyon. The smelter there has actually installed a tellurium plant. They're going to produce about 20 tons of tellurium a year. The plant is costing, I believe, $1.9 million. The tellurium they're going to sell per year makes about $1 million. So they'll make that money back in 2 years. 2.5, 3 maybe. But it's that kind of thinking and that knowing about the ore body at Bingham that Rio Tinto have, and enables them to make those decisions. It's like, let's do this. We can not only look good, but we can also generate some money. And I think mining companies like looking good, and they also like generating money. So that's a win-win for Rio Tinto there. So what now? To kind of wrap up this fairly disparate talk I've given, we need more conversation, discussion of this outside of the group here, outside of economic geology, outside of the minerals industry, rather than just saying we need to reduce carbon dioxide emissions. And that's not a good selling point for some people, anyway. Need more research, education, outreach, consideration of these things through policy. So politicians need to realise the implications of what their targets are. Need more open conversations from all sides about this rather than just ignoring it. And you can talk all you want about how we need to combat climate change, how we make policy to achieve this. But if you don't understand and accept the costs of this in terms of mineral and metal extraction, and the fact that you can't just ship it offshore without thinking about it anymore, you're only halfway there. I know Australians don't think about shipping stuff offshore, but you just look around in cities around the globe, whether you go to somebody and you ask them about what they think about mining, the answer is going to be, it's old, it's dirty, we don't need it anymore, we can just do everything by recycling. And that's why we need some more of these conversations. So that's it. If anybody has any questions, I'll stop sharing my screen shortly, but you can always email me, Simon Jowitt. There's not many Jowitts in geology, so it should be fairly easy to find. If anybody wants any papers of this PowerPoint, I'll happily pass it on. There's much more information than I've been able to share in this time, and hopefully I haven't gone on too long. But if you want any more information about this stuff, then please let me know.